Okay. Hi, good morning, everyone, and welcome to this revision session for Quiz 2 of the Reinforcement Learning course of PS Data Science and Applications program of IIT Madras. So, the agenda is basically to cover the main concepts of week 5 to week 8, and thereafter, we pick up, the tricky questions from the PYQs and the GAs, and we solve them. So that is the main part. And like our earlier sessions, this session will be interactive in nature, wherein I will keep on covering the concepts. But wherever you feel you have got a query or any doubt, you can stop me and we can discuss out that. Is that okay with all of you? Yes, sir. Yeah. Okay. Hi, Shubham. Okay. Yeah. So just hold on. I will save this document. So I had shared this document yesterday with all of you, and I had requested that you to kindly go through this so that we can, because time is critical, and so I'll make a copy of this. Okay. So before we start, do you have anyone having any doubt in week 5? Basics, or shall we cover them in the nutshell? Okay, so I will cover the week 5 important concepts. So the first important concept is temporal difference, and in this week 5, basically temporal difference, that is the TD, SARSA, and Q learning, they have been covered. So what is TD, temporal difference? So what we try to do, we try to estimate the value of
Sir, your
ST.
screen is not visible.
Okay, okay. Sorry, I have not shared my screen. Is it visible now? Can
Yes,
somebody
sir.
give me thumbs up? Okay, very nice. Okay. Okay. So week 5 basically covers TD, that is temporal difference, and thereafter it covers two main algorithms of TD, that is SARSA and Q learning. So coming to the temporal difference, in temporal difference, what do we try to do? We try to estimate the value at ST, considering the reward of the next step and the next state we reach. So the formula is VST is equal to VST plus alpha. Alpha is the learning rate. R is the RT plus 1 is the reward, plus this we gamma. Gamma, we have got to basically control how much I want to give importance to the next step. And then VST plus 1, what is the estimate for the next step, minus VST. So now here I will try to cover some important things here in this formula for basic understanding. So VST is equal to VST plus alpha into RT plus 1 plus gamma into VST plus 1 minus VST. Okay. So remember this part which is known, this is the TD target. TD target. And this full value is known as TD error. Okay. So if any question it comes, so we should know what is TD target and what is TD that. So what happens from ST, I take action AT, I reach ST plus 1, I get reward R. Now considering this, now I update the value of ST. So that is the basic essence of TD error. Okay. Now, so now we come to SARSA. SARSA is nothing. SARSA is a on policy TD control. So SARSA stands for state action reward state action. So what happens here? So in both it is straight away. This is nothing. SARSA is nothing but your TD0. TD0 means that we are covering only the the next step. So that time it is known as TD0, and in week 6 we will see TDN steps also. So SARSA is nothing but TD0, where we are considering only the next step. So and we update. Okay. So now, uh, so already I have covered state action reward. Now in SARSA, there are very, very important things conceptually. So I will cover that also here. And they have been checked in GS and PS of week 5. So QSTAT is equal to QSTAT plus alpha into RT plus 1 plus gamma QST plus 1. And I will write here A prime. Okay. And I will explain what is this. Oh, sorry, this is not plus, so this is minus Q, S, T, and A, T. Okay. Now what happens? I go from S, T, I take action A, T, I go to S, T plus 1, I get a reward R. Now when I go here, when I'm taking this step, so then E greedily, I choose an action A prime. Okay. So before the update, what is happening? I reach here and fix A dash E greedily. And now in the next step, I will select ST plus 1 and A prime. Is that clear? Anybody, any doubt in this? Shubham?
Hello, sir. What is the criteria
Okay.
of selecting the A prime?
A prime, we are selecting E greedily. E greedily means, for example, if my E is equal to 0.1, okay, and I have got three actions, A1, A2, and A3. And A1 is my best action. So I will select this A1 with a probability of 1 minus E plus E divided by N, whereas N is the number of actions. Okay, so there is a probability that I can select A1 also, I can select A2 also, or I can select A3 also. So before updating this QSTAT, I am fixing my A dash. And then in the next step, I use the same A dash. Okay, for other
Yes, sir. Got it. Thanks.
Okay, this is a very subtle difference between SARS and Q learning. When we'll come to Q learning, I will explain Q learning also. Okay, and this question has been asked in the PYQs. Okay, that's I just want to cover now. So this is very that we have done. Now, Ravina, if you remember, you had asked this question in the WhatsApp also, that this alpha which is there, this alpha can be constant also. Okay, and it can be decaying also. Okay, so both are there. In a standard SARSA, it is constant. But when we do stochastic learning, then it keeps on decaying. So when we visit the same state, then alpha will become alpha is equal to 1 by k plus 1.
So,
Okay?
sir, if we consider this as the equation which we have learned in the earlier weeks in week 1 and week 2, it
Yeah,
is it is just having this gamma q s prime a prime terms difference. If it
yeah,
is not there, then the whole equation became the same.
yeah.
So it is just adding the bootstrapping term, I think.
Yes, yes. But remember, just for the concept, that in standard SARSA, it is not decaying, it is constant. And if you revisit your programming assignment 2, where we had done SARSA and Q learning, and if you see your code, we are not decaying there. Okay?
Okay, sir.
Okay. So in a standard SARSA or Q learning, we are not decaying. But when we do stochastic learning, in case it is given in the question, then we should remember that alpha is getting decayed. Okay, that is the important part.
Yes, sir.
Okay, okay. Now we come to Q learning. So Q learning is so this is the formula. QSA is equal to QSA plus alpha R plus max A prime QS dash A minus QSA. So this is the basic difference. So this is the difference between SARSA and Q learning. Okay. So what happens in Q learning? I'll just tell you. So here what happened in Sarsa, we fixed A dash and we selected the same A dash for the next step. In Q learning, what happens? Q learning, I am in a state ST and I take action AT. Now here this AT which is there, this is selected E greedily. E greedily. It means if I have got three actions A1, A2, A3 and A4, epsilon is zero point 0.1. The values, if I consider it is 0 0.1, 0 0.3, 0 0.5, 0 0.2. So A3 is the maximum. So probability of selecting A is equal to A3 is equal to 1 minus epsilon plus epsilon over n, which becomes 1 minus 0 0.1 plus 0 0.1 over 4. So this will become 1 minus 0 0.1 plus 0 0.025. So this, so here when I select this action, I am selecting E greedily. And when I go to the next step, QSTAT plus alpha RT plus 1 gamma. Here I select for the next state where I'm reaching, I select the best action there. Okay. So this is the difference of in Q learning. And so what we can do, what we can say if we ask that this behavior which is there, this is controlled greedily or it is, whereas your evaluation which is there or the estimation which is there, this is done greedily because we are selecting the best action. Is this concept clear? Any question on this? Anyone?
Clear, sir.
Okay. So these are the three main concepts of week 5. Now with this concept, I'm telling you, we can easily hack the questions. But before moving, we will take some questions which have been frequently asked in the PYQs and we solve them to know. Okay. So this is a question, for example, from our GA or PA. So this is a very important question and we can solve this. Today we have got enough time, so don't worry about the time. We'll keep on revising and we'll keep on solving the questions. So anyone, any doubt in this question? Or do you want me to solve this? Ravina, any doubt in this question?
So my theory is also not completed. Questions I haven't reached.
Okay, okay, no problem. So these three concepts are clear from week 5. I think you have done revision of week 5 and week 6.
Yes, sir.
Okay, okay. So the question is, we have been given a trajectory. We are starting from A, we go to B, get a reward of 2. From B, we go to A, get a reward of 1. And from A, we go to C. C is the terminal state. We get a reward of -1. Okay, so this is the trajectory. We have been given learning rate. We have been given gamma. And we have been told that this is TD0. Okay. Now we have been asked what is the value of VA at the end of the trajectory and the VB also. Okay. So what we do initially, we do VA is equal to VB is equal to VC is equal to 0. We initialize. Now remember, C is the terminal state, so VC will always be 0. Okay. So this is the first step logically. Now what we do, we start
So
the
it
trajectory.
is written in the question that the initial value of V A and B are zero, but not C. And you have taken
C
C also initial as zero.
See, always remember, Ravina, this is a very, very important concept. For a terminal state, your V and Q is always 0.
Okay, sir. Sir, for initial. Okay, sir.
This is always 0. Okay, remember this. Okay. Now we start the trajectory. So we go from A to B, get a reward of 2. So what will happen? VA is equal to VA plus alpha into R plus, so this is a TD0. TD0 means it is SARSA. Okay, gamma into VST plus 1, which is VB minus VA. So this is the, now plug in the values, current values, 0 plus 0.1, reward is 2, 0. This is 1 into 0 minus 0. So this becomes 0.2. Okay. Now we go from B to A, get a reward of 1. Now VB will become VB, which is 0 plus 0.1, reward is 1. Where we are reaching? We are reaching VC, so that is 0 minus 0. So this is 0.1. Now, um, is this okay? This one, or there is some 0.1. Okay. Now fourth, we go from A to C. We get a reward of -1. So here now we will use the VA value, which is we have already got 0.
0.2.
Yeah. So now the new VA will become 0.2 plus alpha. Sorry, here I have made a mistake. Here is the BA. So here I should have taken 1 into 0.2 minus 0. So this will become 0.12. Okay. Now here I'm going to see. So reward I'm -1. This becomes 0 minus 0.2. So this will become 0.2 minus 1.2 into 0.1 minus 0.12. So this becomes 0.08. So the value after one episode, VA is equal to 0.08, VB is equal to 0.12, and VC is equal to 0. Is that okay? How to solve it? Any question in this?
Yes, sir.
Yeah. Okay. Okay, very nice. Okay, let's see any other question. So this we have solved. Okay, now we go to any other part.
So there
There
is
is,
a concept of first visit Monte Carlo and
yes,
every
yes,
visit.
we will come to that. Don't worry, we will not leave anything. Okay. This question is clear, or shall we solve it? This question has been asked in PAs and GS. So we will cover
Sir,
this question. Yes, Shubham.
why are we taking the worst action for the S2
Where,
in
where?
this question?
Because
Yes.
it's given in the question,
Sir,
no?
in this question about north, south, and
North,
yes,
south. Huh? So
yes.
see, so we will just go through the question. Okay, don't worry. Okay, what we can do, we can open our course site also. Where is the course site? This is. Mhm. Okay, we'll copy from here only. Don't worry. So first, let's set up the question. This we have done, and they have asked this question. Okay. So let's understand the question first. Okay. So we have to see the setup. So what is the setup? Consider a grid world with deterministic transitions and unit reward of -1 for all time steps. Sarsa is there. The current estimate for the action values of certain states are displayed in the figure. So for S1, these are the four actions. The values are given. So this is north, east, west, south. Similarly here, north, east, south, and west. The agent is currently in state S1. It is here. The policy is E greedy, that E is equal to 0.1 with respect to the current estimate of the action values. The action to be executed at this time step in episode is north. So already they have said that it has taken an action north. The action that agent has committed to take from the next state means S2, in this episode turns out to be the worst possible non-greedy action. So the worst action is which will be what? This is the action. So this is the setup. Okay. So what will be the next action taken by the agent in this episode? So they have already said next action will be the worst action. So it will be west with probability 1. Okay. I hope this is clear. So this is given in the question.
Yes, sir. It's clear.
Yeah. Okay. Now, okay. Now there is a question of importance sampling also, though it is covered in week 6, but we will cover this also here only. So what is importance sampling? So, I am expecting a question on importance sampling. I don't know why I am getting some kind of intuition, because in PYQs they have not asked. So what is basically the concept of importance sampling? See, we have got some pi policy, okay, but we can estimate pi by seeing the behavior of other people, which is known as mu. Okay, both are looking same. So remember here, I will cover some concept which will help you in some other questions which have been asked in the PYQs. If pi for any action ST80 is greater than 0. For example, they can give any value 0.1, 0.2, 0.3, anything. And remember, the pi is nothing but a probability. Then the mu, that is the behavior in ST or AT, will always be greater than 0. This is applicable. That if pi is greater than 0, then mu will always be greater than 0. This is the first concept, number 1. Number 2. So, in case they tell you a question which they have asked in a PYQ that pi ST80 is 0.3, then what can be the value of what can be mu? So mu, we know mu will always be greater than 0. And this is a probability. So this is bounded by between 0 and 1. So I have asked a question in the discourse that why it is not less than equal to 1. I'm waiting for that reply. I think Rohit has replied. I'll just check. So there is a reply to that. Rohit Kumar, yes. Okay, my TD0 is right. He has given an answer. So I had asked a question. And Anupam has asked. So okay, in this question it is less than 0. Okay, so in that question, in that particular question, it is less than 1. So this is the relation between pi and mu. Now we come to a concept called importance sampling ratio. So importance sampling
So
ratio.
why it was not equal to 1, sir?
We
I
will
didn't
come
get
to
it.
we will come to that question because there were 4 actions in that. Okay, we'll see that. Let's see this. So rho, the importance sampling ratio is product of pi divided by product of mu for all conditions. Now with this, we approach this question In the question, they have given compute the importance sampling ratio for the trajectory shown in the figure if the behavioral policy is equiprobable random policy. So this is a very, very important thing, equiprobable. It means all the actions can be taken with 0.25. And the target policy is pi as shown in the figure. So see, this is the target policy. This is the terminal state. So here we start. This is 0.9, again 0.9, again 0.9 and 1. So product of pi is equal to 0.9 into 0.9 into 0.9 into 1. Now when we consider mu they have said that equiprobable random policy. So for mu this will become 0.25, this is 0.25, this is 0.25, this is 0.25 and this is 0.25. So the denominator will become mu, product of mu is equal to 0.25 into power 4. And when we do this, we get an answer. Okay. So that is the how to solve it. Now, when we know importance policy, this importance ratio, importance sampling ratio, then we can calculate something called summation of rho into GT divided by summation of rho. For example, we don't know pi. What is pi? But by comparing the policy which is there here for a particular trajectory and then behavior, then we can estimate a policy. So this is the formula. So these are all four major concepts for importance sampling ratio. Okay. Okay. Now again, there is a this question is PA based on SARSA and Q learning. So anybody any doubt in this question, or shall we solve it, or we can leave it because we have to cover other weeks also?
Sir, leave it, sir.
Okay. So only remember this. What is the important thing which we have to learn? So this is a Q learning is in this setup. Unit reward is -1. Epsilon is 0.01. The action A sampled at this state. So what it happens, what they have given, that from S1, perform one update of the action value for the pair S1A. Use alpha is equal to 0.1, y is equal to 1. Okay. Now from S1A, it will go to S2. And what is the best action in S2? -0.7. Because that is the part.
Yes, sir. Max, it will choose a -0.7.
Yes. Now, also they have given the action A sampled at this step in the episode is greedy action. It means that from S1, what I'm doing, I'm taking the best action. So I'm taking this action. So this they have given. Otherwise, in Q learning, it is done by E greedy. Okay, but we have to read the question. We are taking a greedy action. So we reach here S2, and there we take the max. So we have to apply all this formula which is there. So QSA is currently is -1, alpha is 0.1. I get a reward of this is 0.1, reward of -1. Gamma is 1. Here is gamma. And max here is 0.7, -0.7. So this I plug it here. And -1 here it becomes. So this becomes -1.07. Okay. Now a very important question they have asked. What will be the next action taken by the agent in this episode? So just now we have covered these concepts. Can anyone answer this question? It is a Q learning. So what will be the new action
East, I
from?
think.
Huh?
East action, I think.
Why? What do we do in
Because it
Q?
is the max for the
In
S2.
No, in Q learning, always remember this QSTAT which is there. This is taken as E greedily. Okay. Whereas in SARSA, we take the action which was fixed in the earlier episode. It is already fixed. So here we will take. But here in Q learning, we will take the best action. Best action is minus 0.7 with a probability of 1 minus E plus E by N, and rest all other actions by E by N. Okay, please remember this.
Okay, sir.
Okay, yeah. Okay. Now, this is the question which Ravina had asked. So, this question is frequently asked in the PYQs. Every PYQ has a similar kind of question. So, we'll solve this question. Monte Carlo TD0, how to make an MDP from this. So, let's copy this and then we'll paste it. Okay. So, let's see first the setup. Consider an undiscounted episodic. So, undiscounted means gamma is equal to 1. And we will solve also some question where gamma is this it is a discounted. We'll solve that, or maybe we can solve it here also. So we will take one examples where gamma is 1 and where gamma is 0.9. So first we solve for undiscounted. It has got two non-terminal states AB. Rewards are binary 0 or 1. The following are the some episode experienced by an agent following by a fixed policy. The terminal state is not explicitly mentioned. So these are the episodes 1, 2, 3, 4, 5, 6, 7, 8. And the first they ask what is the estimate of VA and VB by first visit MC. So how do we approach this problem? So in the first visit MC, what happens? We have to understand the concept. I will just copy this here for the first MC. Okay. So in the first MC, let's calculate for VA. VA, and here we will cover VB. So here VA is nothing but 1 plus gamma into 0 is equal to 1. Here it is 0 plus gamma into 1 is equal to 1. Here it is 1 plus gamma into 0 is equal to 1. 1 plus gamma into 0 is equal to 1. Rest A is not there. So what we get? VA is equal to, we sum it, 1 plus 1 plus 1 divided by 4 is equal to 1. Is this okay with everyone?
Yes, sir.
Okay. Now VB, you see, VB first step it has got 0, next step 1, next step 0, next step 0, then 1, then 0, then 1, then 1. And how many times it is coming? 8 times. So this is 4 by 8 is equal to 0.5. So these are your MC updates, VA and VB. Now when we do for the batch TD, so for batch TD what will happen? I'll just change the color. Batch TD. So for first episode, we have to write VA is equal to, just hold on now, receiving a call. Hi Baljit ji, Jai Hind. Can I give you a call maybe after 1.5 hours? I'm in a meeting. Yeah, okay, thank you. Okay, so here we can write this VA is equal to reward plus VB. Second, we can write reward plus VB. Third, we can write 1 plus VB. Fourth, we can write 1 plus VB and divided by 4. So this will become 3 plus 4 into VB divided by 4. And VB which is there, VB is not going anywhere. We are stopping at VB. though they are not terminal states. So VB remains 0.5. Now, if we place it here, it will become 3 into 4 into 0.5 divided by 4, which becomes 1.25. Is this okay? MC and batch TD with everyone? Any question in this?
Hello, sir. Could you please explain batch TD once?
Yeah. So batch TD, what we are doing in Monte Carlo, we take only one is we take the value. So value is reward plus gamma into next state.
Yes.
So we consider what we do. We consider calculate from every episode. Whereas in batch TD, we are not taking this. We are considering this VAR plus gamma into VB. Okay, so we are taking in a batch.
Mm-hmm.
Okay, okay.
Okay.
Whereas in MC, what we are considering this value which is there already, which is given 0.
Okay.
Okay, okay. Now we'll explain how to find an MDP. This is a very important thing. It has been asked in the PA, GA also, PYQs also. So see what is happening in this question. From B, from B, what we are going to not going anywhere, we are going to terminal only, you see. But how many ways we are going? In 4 times we are getting 1 reward, and 4 times we are getting 0 reward.
So 0.5 probability both ways, is it?
Probability will be 1, because in, see, in all conditions, where B is going. So this can be represented as B to T, probability is 1 and reward is 0.5. We can write it like this.
Okay, sir.
Is that correct or not? And see here, A also, in all conditions, it is going to be only. In 3, it is getting 1, and in 1, it is getting 0. So this can be written as A going to B with probability 1, but reward of 0.75. Is this okay? Any question on this? Okay, we'll solve some other questions also to get this. So what we did for Monte Carlo, then we did for TD batch, and then we made a finite MDP. We'll solve some questions of the PYQs also. Okay. Now let's go to some question. This
Hello, sir.
yes,
Yes,
yes.
I have doubt in the above question.
Yeah, please ask me.
So in the green font, when we are finding the VB, why we are averaging it?
Which one?
The green font on the right, VB.
So VB in the Monte Carlo, if you remember, we take all the values of all the episodes and then we average it out. And in the batch TD also we do the same.
Uh, but sir, on the left, we are finding VA with the normal updation rule.
Yes, so in Monte Carlo, what we do, in batch TD, when I'm doing for A, I'm not aware about the value of VB in the TD. In Monte Carlo, I use only this episode. In TD, I'm taking the all this thing in one batch, and I'm considering that I'm not aware about this VB. So I'm just going R plus gamma into VB. Whereas in Monte Carlo, here I know that next state of B is 0. Okay, here it is 1. Here it is 0. Here it is 0.
Okay, sir, got it.
Okay. Yeah. Okay. We'll see some other questions also. We'll solve 3 4 questions like this. Okay. Now this already have covered that whenever pi SA is greater than 0, mu will also always be greater than 0. This is a very important question.
And sir, the reverse need not to be true now.
No, no, reverse is not need not to be true.
Yes.
Okay, because behavior it might be showing, but it may not be your actual policy. Okay. Okay. Now we come to week 6. So week 5 we are done. Week 6 we will. So week 6 start with n step TD. So in TD0 was what only we were considering only. I'm covering the only the TD error. We are covering only R plus gamma into VST plus 1 minus VST. So here in n step, what do? We consider this n. So R plus gamma into VST plus 1 plus gamma square VST plus 2 plus it keeps on going. It will go y up to n and VST plus n. So this is the formula for n steps. Now, what are the advantages? What are the disadvantages? The advantage is that your variance which is there, your bias which is there, you are reducing the bias. So it is more accurate. The disadvantage is there that it has increased variance and it requires more memory to store. Okay. Another important point that if your n becomes 0, then it is TD0. We can see in the formula. And when n is equal to t, that all the episodes, then it is a Monte Carlo. It means that we have to go through the entire episode to find the value. So these are important questions for objective kind of questions. Now in TD lambda, what do? We consider this. So this is GT1. So we consider 1 step also, we consider 2 step also, we consider 3 step also, and we consider GTN step also. And the formula for TD lambda is GT lambda is equal to 1 minus lambda summation lambda is equal to 1 to infinity lambda n minus 1 GTN. This is a very, very important formula. Please remember this. Okay. So advantage of TD lambda is that it has got low bias also and it has got low variance also. Whereas when we were doing only, estimating this n step, so we had high variance. So here when we do this TD lambda, we reduce the variance also. Now, what happens? There is a disadvantage that we have to complete this entire episode to update if we consider this formula. So how to solve it? What we do, we have got a concept of eligibility trace. What we do, we reach a state and then we keep on updating the eligibilities of the previous states, decay, and then we update these states. So at every step, whenever I'm going, so I will cover, I had shared one example also yesterday with all of you, but I will just cover the concept so that your concepts are clear. So TD lambda with eligibility trace. So for example, we have got 3 states, S1, S2, S3, and then we have got a terminal state. Here A1, A2, A3, R1, R2, R3. So what do we do in TD lambda? Number 1, initialize all Vs is equal to 0 for all S belonging to S. So this is the first step. Okay. Now start first episode. When we start first episode or for any episode, initialize E s is equal to 0 for all s belonging to s. Okay. So now in the starting is vs1 is equal to vs2 is equal to vs3 is equal to vt is equal to 0. Vt will always be 0. So we are interested only in vs1, vs2, vs3. So now here es1 is equal to es2 is equal to es3 is equal to 0. Now, in eligibility, we have got certain parameters: learning rate, discounted rate, and lambda, which is the TD lambda. So, what happens now? So, start first episode, we have gone there. Visit state S. Visit state S. So, for example, here we have gone to S1. And you take action A1, get reward R1, and you reach state S2. Visit state S, take action A1, take reward. Calculate TD error. Calculate TD error. So TD error is equal to R plus gamma into VS2 minus VS1. So this is your delta. This is A, B. Update, update your ES. So ES1 is equal to ES1 plus 1 is equal to 1. Now, remember this chronology. This is very, very important. Now, what you do, you update all other states, all states now, all states values. And formula for that is Vs is equal to Vs plus alpha into TD error into E of S. Okay. So now see here what is happening here, that n state S1, I am also updating for S2, S3. So when I'm at S1, I will not be able to update S2 and S3, they will remain 0. But when I have reached S2, I will update VS1 also. Similarly, when I reach S3, I will be updating S1, S2, S3 also. So I don't have to reach the final episode. I'm updating this value at every step. And second step is now I decay. So update S, this part, and second part is decay ES. And for that formula is equal to ES is equal to lambda into discounted rate into ES. And you keep on doing this until we reach terminate when reach terminal state. This is for episode 1. Now for second episode, again initialize ES is equal to 0. VS will not be 0. Now VS will keep on taking the values which have been updated. But for every episode, ES will be 0. Is this okay with everyone?
So in the first case, the B part, the updation rule of ES1 is equal to ES1 plus 1. So that we are doing when we reach the state S1, is it? And not for all the states.
No. So this is only for the state where we have visited state.
And that the decay part is for all the non-visited states,
Decays for all, including visited.
including visited. Okay.
Yes.
So sir, it's like the epsilon greedy one case,
Yes.
similar to that. Yes.
Yes. Okay. So remember this chronology, how it is happening. So what we do, we initialize VS is equal to 0 starting. We start first episode, we initialize ES is equal to 0. Now we visit one state, we take action, get reward, calculate TD error. Now what we do, along with this TD error, we update the ES1 for the visited state. Now, after this, update the all states, including VS1, VS2, VS3, and now decay ES for all. Okay. Terminate when we reach terminal. Now, for the second episode, again initialize ES is equal to 0. This is all eligibility trace. Okay, I have shared the example of, the example they have not given in our course material or in any GA. So I have covered that. So you can go through that example, things become very, very clear how it is happening. Okay. So this is all about week 6, eligibility trace, TD lambda algorithm. Okay, so see, Ravina, just pay attention. Same it is here. Initialize S. So here what they have done, this, see here it is a misprinting. That's why professor had written here that this ES will come here for every episode. Here ES is equal to 0. So this ES is equal to 0 is not here. VS is equal to 0 initial. For every episode, ES is equal to 0. Initialize S, take action A, get R, and calculate TD error, and update ES for the visited. Now for all S, update VS, and for all S, decay ES. So you're updating by one, and then you're decaying also. That is very important.
And sir, what about it's one of the variant? I don't remember the name now.
Uh, okay, we'll see. But okay, but I don't recollect any variant covered. If I'm not wrong, they had covered expected SARSA, but not the TD lambda. Okay. Now, in the same now week 6, they have also covered the maximization bias and double Q learning. So what is a maximization bias? That in Q learning, what keeps on happening, that QSTAT is equal to QST plus AT plus alpha into R plus gamma max A QST plus 1 A minus QST AT. So this maximization, that every time we are using this max, so due to this, what happens? A maximization bias comes.
Bias comes.
Okay. And now remember, this bias, maximization bias, is also there in SARSA. In SARSA, but less than Q learning. Okay. So number 1. Number 2, in presence of maximization bias also, your algo will converge, but will take more steps. Okay, so these are the important points. More steps. Now, what is the solution? Solution is that we keep two values of Q, Q1 and Q2. Okay, and when we are updating, we update with probability 0.5. We update Q1 is equal to Q1 plus alpha into gamma, R plus gamma. And here, instead of max, what I will do Q2 ST plus 1, and action I will choose argmax A from Q1 ST plus 1A and minus Q1. Else means that again probability of 0.5, or I will update Q2 and you just reverse the values.
So, sir, does it mean that action we are taking from Q1, but the reward is taken for that action which is chosen with respect to Q2?
Yes. So remember what is happening. So this action, this is the action, target action. This is the target action. So for Q1, target action is coming from Q1 only. Okay. For Q2, target action is coming for Q2 only. Okay. And if you see my notes, I have given an example that how does it work. So see, professor had given one example that you go to right, you get reward of 0. If you go to left, you get a reward which is n 0.1 and
Normally
minus
distributed.
1. So what will happen, that when you are taking max, always you will go towards here only, whereas the correct way is to go here. Okay. So when you happen take q1 and q2, so what will happen that q1 and q2 which is there, when this is negative, you know, this is negative, so both being positive will not be chance will not be there. So that's why you're doing this. Okay. Okay, so let's move fast again slightly. So I have covered maximization bias, I have covered double q learning. Okay, so this is there. So in week 6, those questions are not there, but I will encourage all of you. So there was a question about this where the answer is incorrect. So we can see this question before moving further. So they have asked which of the following is the correct coefficient of GT T minus T minus 1. So we just have to use the formula. So we know GT lambda is equal to 1 minus lambda summation lambda n minus 1 GT n. So here n is equal to T minus T minus 1. Therefore, coefficient will become 1 minus lambda into lambda T minus T minus 1 minus 1 is equal to 1 minus lambda into lambda T minus T minus 2. This is the correct answer. Okay, that's why it was none of those. Okay.
So
Now,
I have a doubt in with the same in TD.
uh,
In group they were discussing the difference between TD0, TD1, and TDN. So the TD0 and TD1, I'm confused between them. And if we TD0 is if one step ahead, then TD1 should be two step ahead. Then TDN should be n plus one step ahead, sir. So why it's not like this?
so let's see. We will say TDN formula. TDN formula is R plus gamma into VST plus 1 plus gamma square VST plus 2 plus keep on going gamma n VST plus n. Is this okay?
Yes, the formula is this
Yeah.
only.
So when n becomes 0, your TD becomes R plus lambda into V into ST. Huh? So this is nothing but TD0. I will cover some other important point which might come in the question paper. Okay. See the formula for GTN is equal to, sorry, GT lambda. GT lambda is equal to 1 minus lambda summation lambda n minus 1. N is equal to 1 to infinity, and this is your GTN. Okay. Now we know that when we have an episode, it does not go to infinity, it will terminate at some time. So if you take a case where you have got S1, you have got S2, you have got S3, and then you terminate. Okay. So then what will happen? How will you calculate this? Can anybody answer this? You get R1, you get R2, you get R3, action A1, A2, A3. Ravina, can you answer this?
So, so there are three states. The
Okay. Okay.
so
What you
I
do,
don't.
for example, you take lambda is equal to 0.2, for example. Okay. And then you take R1 is equal to 1, R2 is equal to 2, R3 is equal to 10, For example, for this example. So what happens? See, though this formula says it is up to infinity, when we reach a terminal state, so this all future values which are there as G4, G5, G6 up to infinity, they will be equal to your last VS3. Okay, that is very, very important. Now, when you plug in this formula, GT lambda is equal to 0.8 into summation 0.8. So n is 1. So this becomes 0. This becomes GT1 plus 0.8 GT2. 0.8 square GT3. Now after this 0.8 cube GT4, 0.84 GT5, and it keep on going, this formula. But we know that our this has been terminated here at GT3. So all these values GT4, GT5 and all future values will be GT3. So this we can write as 0.8 into GT1. GT1 we can calculate. Okay, for example, we have been given some gamma is equal to 1 also. So GT1 we can calculate. We will find some value. We will, for example, we get a value of 1. Here we get GT2, we get for example, 2. Now this 0.8 square, this GT3 we calculate, and now we do this 0.8 square plus 0.8 cube plus 0.84 plus this. And now we can calculate. So we have got all the values. We have got value for GT3 also, for example, for just an example I'm taking. For example, it is 10. And this X we can calculate just by doing X is this, and then X into 0.8 minus X minus 0.8 will be 0.8 square. Therefore, X is equal to 0.8 square divided by 0.2. By doing this calculation, you can get this. So this similar kind of question has been asked in a PYQ. So concept is that only, that though this formula is up to infinity, but when we terminate, all the future values of the GTs are same to the last GT value. So here in case GT4, GT5 and all future values will be equal to GT3. Is this concept understood, everyone? Any question in this?
Sir, that X part is not clear.
X, okay, X is very easy. Okay, see X is equal to, we'll take 0.8 square plus 0.8 cube plus 0.84 plus keep on doing this. Now what do I do? I multiply X with 0.8. So this will become 0.8 cube. This will become 0.84. This will become 0.85 plus all that. Now when I subtract, this will become 0.2x, and this will cancel this, this will cancel this, this will cancel this. Everything will be cancelled and remaining is 0.8 square. Therefore, X is equal to 0.8 square divided by 0.2. Is it okay?
Yes, sir. All right, I got it.
Okay. Thank you. So before we move to week 7, can we take 5 minutes break? I will have a glass of water, please.
Yes, sir.
Yeah.
Fine.
Thank you. Thank you. Yeah.
Thank you.
Just. Hi, shall we restart? Can somebody give me a thumbs up?
Yes, sir.
Okay, okay, okay. Now we come to week 7. So, week 7, what it starts, it says that, till now, up to Q learning, SARS, TD, and all that, what we were doing, we used to store our values in a grid. Okay, so we are storing the in the grid. So we have got some state, and as per the actions, we have got those values. Now, when our state and action, this space becomes very, very large, then this is memory explosion. Okay, number one. Number two, here it is handling only the discrete values. But in case your state or action is continuous, for example, you have got a autonomous car. Okay, autonomous car. So your state, for example, speed is your continuous. And your action, for example, how much brake to apply or how much to turn, that is also continuous. So that cannot be, sampled here. Number three, that this cannot be generalized, which is the most important consideration for considering that instead of having QSA, why don't we make this QSA of some function of SA and parameterized by value theta? This is the most important thing of week 7. Okay, that we, this value which is there, QSA, we make it as a function. What happens now, this function can be a linear approximator, that we have got SA, and then you multiply by some W's. So SA is something like this, 0, 0, 1, 0, 0, 0. Here there are some values for W1, 0, 0, 1, 1, 0. And when you multiply this, you get an answer, Q. So one, this is linear approximation. Okay. The second is, you can also use a neural network. We have seen the neural networks. We feed S and A to neural network. We have got various layers and we get Q. And the most important thing is here is that when we do this, then we can update weights through gradient descent. Gradient descent. Okay. Now, how to do that? So we have said that QSA is some function of SA theta. Now, when we know that when we have got a function like this, then we can update this theta t plus 1 is equal to theta t minus half learning rate q star SA minus this FSA theta or QSA square. This is your loss function. Loss function. Okay. So this QSA is nothing, your function as a theta, that as per your present theta, what is the value of QSA? Q star is a target. The problem is that we don't know Q star. We don't know Q star. So what do we do? In place of Q star, what we use? We use TD target. Okay, and what is the TD target? TD target is reward. What is the reward we got here? Plus gamma max A Q S T plus 1 A. So this formula, which this becomes, so if we write here this theta T plus 1 is theta T minus of alpha JT, where JT is function. Okay, this JT is the entire. Now JT is equal to R plus gamma max Q S T plus 1 A minus Q S A whole square. Is that okay? This one? Now I can write down this JT is equal to R plus gamma max Q S T plus 1 into A minus, this is a function of SA and phi.
Sir,
Yeah,
sir, but max function is non-differentiable. Then how we are taking
yeah,
gradients?
yeah. And so we'll tell you now. We'll tell you. We have not reached here. Once we come to the river, we will find a way to how to cross that river. Okay. Okay. So now this QSA which is there, it is nothing but phi of SA, and we are multiplying this with theta. We had seen here. We had seen here QSA. We are multiplying here, and we are getting an answer Q. So what do we do here now to answer your question, Ravina? We do something called partial derivative, partial gradient, partial gradient. And what do? We consider these two values as constant. So when we take delta JT by theta, it is square. So this will become 2 into delta. This entire term we can write as delta. This is delta. And when we take derivative of this with this will become minus 1 into phi. So this is 2 delta minus 2 phi. Is this okay?
So, sir, the TD error term, no, that max term, that is totally taken as
Constant.
constant. That
Constant.
will be
Yes.
0.
Yes. So now you fit this in this formula. Your theta t plus 1 will become theta t minus half into minus 2 delta alpha into phi. So this becomes theta t plus alpha into delta into phi. This is the important thing. Is that okay?
Yes, sir.
Yeah. Okay. So this is the most important derivation and to understand. Now we have to understand what is this phi. Phi तो मैंने आपको बता दिया, लेकिन phi है क्या ये? तो phi क्या होता है? For example, I have got 4 states: S1, S2, S3, S4, and I got 4 actions: A1, A2, A3, A4. Now can I write this? So I will have combinations what? S1, A1, S1, A2, S1, A3, S1, A4. So I will have 16 combinations. So can I write S1 as 0001? This as, or just hold on. This I write 1000, 0100, 0010, S4 0001. A1, either I can write 1234 or I can do this also 1000, 0100, 0010, 0001. Now all these 16 combinations now can be written, for example, S1A1 phi is equal to 1000, 0001. Okay, this is phi. Now I know Q is equal to phi transpose W. So what will be W, dimension of W?
8.
Yes, very nice. So this will be 8. in case of linear approximation. Linear approximation. So what do? I multiply this 1 0 0 0 0 0 0 0 1 transpose, sorry. This will be 1 0 0 0 0 0 0 1, and now I initialize this W some value. I don't know, but I'm initializing. So I initialize 1 0 1 0 1 0 1 0 1 0, and I get some Q. Now with this Q, now I update WT plus 1 is equal to WT plus alpha into delta, this TD error into phi. This remember. Okay, this question has been coming in all PYQs. This calculation will come, and it will consist of around 3 questions. Okay, we'll see those questions. But you first have to understand the concept. So is this concept clear with all of you?
But sir, in this question, in this equation, we saw that it was consisting one term with a squared term. So why it is known as linear approximation? We are getting a quadratic term in the equation previously we saw.
So Ravina, in machine learning also, in machine learning, when we were not doing, in machine learning models like linear regression and all that, what do? We do linear approximation only,
Oh, yes.
but your loss function which is there, it is a square.
Okay. Yes,
Okay.
sir.
So
MS.
so that when you take a gradient of this, we can take a gradient. Okay.
Mm. Yes,
Okay.
sir. Got it, sir.
Yeah. Okay. Okay. Yeah. Okay. So these are the main concepts of your week
Hello,
7.
sir.
Yes. Yes.
I have doubt in this
Yeah.
binary question. Here's a slide.
Yeah.
Sir, why the pi of S1 and A1 is equals to some binary value of 8?
Just hold on. So please, you can mute your speaker. So I just gave you an example. I just gave you an example that how can you represent the states? How can you represent the states? See, when I have got a state, for example, I have got a state like a robot is there, okay, and it has got 4 states. One is terminal state. So I have to represent those states. So what I can do, I can represent this is S1, this is S2, this is S3, this is S4. I can represent this state as 001, okay, 0100 0010. Like in machine learning model, we used to do one hot encoding for the your categorical
Yes, sir.
columns.
Yes.
Okay, so what I'm doing one hot encoding for a categorical column. Okay.
Okay, it's clear. Sir.
Okay, similarly for action, there are 4 actions: north, south, east, west. Again, I'm doing one hot encoding for that. I'm just representing that.
It's clear, sir. Thanks.
Okay. Now with these concepts, straight away we will jump into solving questions. Okay. So concept is clear. Now there is a another very important part was there that will come. I think in week 7 only is there. Okay, so this I have covered already. So important concept I have covered. I have derived all these things. So when we solve the questions, your concepts will become much more clear. Okay, so these are the representations. We are doing one hot encoding, and this was for linear approximation. Okay, now there is a two methods called codes and tile methods. There will be questions on that also, and we have got questions in PAs and GAs also. So, what is the main concept of this code and all that? So, what happens in actual world that we have got a grid? Okay, we have got a grid. So, generally, what do we do? and we have got these states and we have got actions. Okay, S1. So in actual, what we do naive method. I'm covering naive method. So what do? We make some this that for this the q value will be sum. For this blocks the q value will be this. For this blocks there will be q value. I will update. Okay, and for this I will have q value. Now what happens when an agent jump from here to here? So there is an abrupt jump in the q value. There is an abrupt change in the q value, due to which your convergence will have noise, will be noisy. Okay, it will be jumping. So this is the name method. This is clear with all of you?
So the values in this particular region are same.
Yes.
Okay, sir.
Okay. Now, so the first method is known as course method. So in course method, what do we do? Course method, what do we do? Again, we take this grid and what do? We select some circles. So there is one circle here. Then there is another circle here. And there is a third circle here. Okay. Now when we represent, so see, for example, this is S1, this is S2, this is S3, this is S4, S5, S6, S7, S8. So now every state can be represented as, now we have got three circles. So I can represent every stage with three values. So S1 has got only the red circle. So it will be 1, 0, 0. Okay. S2 also will be same. S5 will also be same. But when you see S6, S6 which is there, so in S6, all the three circles are there. So it can be represented as 1, 1, 1, 1. Okay. So here what happens when an agent jumps from here to here. So see, S2 also has got both circles. S3 has also got both circles. So when it is jumping, there is no change. There is very less change which is happening. So it can handle this, things again from here. But the problem with the course is that at the boundaries of the circle, again the same problem happens. For example, at boundary from here to here, if it is jumping, then the problems will happen. So for that, the solution is third here, which is tile method. So tile method, what it does, it changes the entire grid into various tiles by keep on shifting. So there can be one tile here. This is one tile. Okay. There is another tile here. There is another tile here. So every state will be at least covered by more than one tile. So that's how we solve this problem. Okay, so this is the tile method. So this is known as, we started from naive, we saw the problem, then we came to course, and then we came to tile method. Now with this understanding, we will solve the questions also. Okay? Is that okay?
Sir,
Yes,
instead
sir.
of the style method, we can come up with a better geometrical shape also now. Like,
Yeah, that has not been covered by the professor, so that you can do research when you do go for your MTech and PhD. Okay, okay. So shall we go ahead again now to solve some questions?
Yes, sir.
Okay. Now in this week 7, there was another one more concept which has been covered. So week 7, concept wise, week 7 is the most lengthy week. So in week 7, they have also introduced something called DQN, and then they have covered some advanced topics also like double DQN, and they have also covered as dueling DQN. Okay. So in the DQN is nothing. DQN is deep Q learning. So in the deep Q learning, this paper came with Atari game. So where they made that they were feeding only the state, not the action. They fed it to two convolution layers. So one CNN and then another CNN, and then they flattened it. Then they had one fully connected layer, and then finally they had one output layer. This was the output layer. And this output layer is all the actions which are there. So for the Atari game, they were 18 this output. So 18 means was like this: arrow, this, 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 this. So these are the 8 positions. Then 8 positions plus fire was another. Then there was again no action was another one, and no input when there is no input. So these are your actions which are there. So when you are what they did, they passed a 84 into 84 4 frames of the game. Why we pass four frames? So that it is a we are passing the screenshot. So when we are passing 4 frames, at least it has got a context what has happened earlier. So to complete the Markov, if we pass only 1 frame, then it is non-Markov because it does not know what has happened in the past. Now, when we are passing these through 2 CNN layers, this is known as feature extractor. This is feature extractor. Okay, here so you can go through the literature. If I'm not wrong, it was 8 by 8, and this was 16 filters here, and stride was 4. Here it was 4 into 4, 32 filters. S was 2, if I'm not wrong. Then you flattened it, it comes around 2596. They had one fully connected layer, 256. This was 18. Now you keep on taking action. So you have taken action this here. Now you do the back propagation, keep on updating all weights. So it did for all, it kept on playing, and it learned all the actions on its own. So this is the basic of DQN. Is that okay? Anything I'm missing? Anybody wants to add on? Shubham?
Shubham is not here.
Okay. Ravina, anything I'm missing? Have you revised this?
sir, I am seeing this first time, so everything is okay from my side.
Okay. So I think I have not missed it. Yeah. So here what we have to see, go through the notes. I will just cover the notes also here. So we'll see whether I have missed or not. Yes, sorry. Mouse is giving me a problem. Okay. So see DQN. So we are passing a state. We have got CNN layer, CNN2, then fully connected layer, then the output layer. Output layer has got 18 actions. And like I covered here, 84 into 84 into 4 we passed. Then we passed CNN 1, 8 into 8 filter, 16 filters. Stride was 4. And you can use this formula which we learned in deep learning, that output is equal to input minus filter size plus 2 into padding divided by stride plus 1. So here we get 20. So we get 16 into 20 into 20 output. And remember, we are using ReLU at both the CNN. Now again, we use 4 into 4 filter, 32 filters, stride 2. So we get 9 into 9, 32. And this 9 into 9 into 32, which becomes 2592, we flatten it. We passed it to through fully connected layer to 56 neurons and to 18. Now when we pass this state and we keep on taking action and do the back propagation in respect of this. So this feature learning happens. So these features which are there, they are nothing but these weights which are there. So you keep on updating these weights. And when we did this, it learned all the moves which are to be made. So this was a deep Q learning. So this is the feature learning or the feature extraction, the CNN and the fully connected. And the last layer, output layer, is the linear feature approximation, because here we are doing just linear feature approximation. So now in this DQN, we had two problems which we faced. So these two problems I will just explain here so that concepts are clear. So there were two problems. When we are passing this 84 into 84, 84 into 84, 4 frames. 4 frames. So what is happening if you take a screenshot and you take 4 frames, these 4 frames will be nearly identical with very, very minor change. So what happens? Their correlation is very high. So this is one problem. Second problem is that your target which is there, it is non-stationary. So to solve this, what are the actions we take? So to solve this, correlation is very high. What we do, we make a buffer. What do we do? All the states, actions, we keep on taking, and reward and S dash, we keep on adding to this buffer. And if you remember in the PA3, we had applied this, we had made a buffer. So and now when we feed, what do? We randomly choose from this, So now it is very, very less likely that whatever we are choosing, they are highly correlated. So we solve the correlation problem. Second, for non-stationary target, what do we do? Non-stationary target. Now the formula is same, STAT plus is equal to QSTAT plus alpha into R plus max over QST plus 1 theta minus QST 80, and this is also coming from theta. So if we are using the same network, what is happening? We are calculating this also target also from here, and we are using this also. So what do we do? For some episodes, we freeze this. We freeze the weights. For example, every 1,000 steps, we freeze the target parameters to make it stationary. Now this is not stationary. Otherwise, what was happening? This was also changing and this was also changing. So your target was non-stationary. So by freezing, we make it stationary. So these are the two concepts how we make the target stationary.
So
Yeah.
can we add a regularizer also instead of the buffer to remove the correlation between them?
But how it will happen? Help, Ravina, tell me. So there is a screenshot. There is a game, Atari game we are playing, and it is like this. Okay, these are two here. Agent is here. There is something here. What will happen? There will be very, very minor changes.
So then from the buffer case, if we select randomly, then we can even select those things which are like like we are selecting which are not correlated, but we can select even from, we can pick a bunch which are totally correlated and highly correlated also. It can be possible in random selection
No,
also.
no. In random selection, the probability will be very, very less. Okay, we are talking in millions of this, millions and billions of this. Okay,
Okay.
so millions and billions of this. So then it is very, very less. Okay, now, so to solve, already I have, you can go through the notes. I have explained in a very, very simple language. Okay, I've written also. So these are this was the DQN concept. Now, so I have also given that we freeze weights. So we, unlike double QN, here we are not using a separate Q1, Q2. For the target, we are just freezing and we are using it. Now, another concept is Huber loss. So in the deep QN, we used Huber loss. So for that, the loss function is basically, the loss is half A square. If A is less than this delta is not TD error. This is not TD error. This is some hyperparameter, for example, 0.1. So if your loss is less than 0.1, then we use quadratic. So this comes this region. And if it is more than delta absolute value, then we use delta into absolute value of A minus half delta. So this gives us a Huber loss, a straight line. So this is Huber loss. Just remember this when question comes. So here this delta is nothing, but it is a hyperparameter. Okay. So advanced value based methods, we can use double DQN also. So the same problem which we had in the Q learning, we will have in the DQN also, maximization bias. So what we do in double DQN, we are applying the buffer because the sample correlation problem is common in both. But and in double Q learning, what we do, we again do the same concept, that the target action we select from here. That Q star theta, which is there, the target value which is there. Now this target value we are updating with at every step. What we are doing, this target, we are taking the reward and we are using the Q theta, which is the network. This is the frozen one. We take action, this state st plus 1, and action we are choosing from target. So you can correlate this with very, very easily. If we keep Q1 here, then we were taking from Q1. So the target is coming from target, and here it was Q2. So concept is very, very same. This is an important formula. We can update the target network parameters. Either we freeze them or we can update them at every step. So we can update the target parameters as 5 prime into tau into theta plus 1 minus tau into theta prime. So this is an important formula. Theta dash is equal to r into tau, tau into theta, which is the present parameters of my neural network, plus 1 minus tau.
And so what is tau, sir?
Tau is a hyperparameter. I can select 0.1, how much I want to give importance. Okay, so I'm giving less importance, for example, 0.1. So I'm taking some values from my present neural network and I'm taking some values from my frozen one, the earlier one. Okay. Any question in this? Anyone? Okay. So we are coming to the last part of week 7. Like I mentioned, week 7 has got many, many concepts. So we started with TD and TD lambda and all that, then DQN, then double DQN. Now we come to dueling DQN. The dueling DQN is a very, very important concept, and it is favorite of the professor, like he had mentioned. So what is the meaning of dueling DQN? In the dueling DQN, what happens that many a times when you are in some state, your actions, they don't matter. For example, you're going on a road, the road is vacant. So whether you turn left or you turn right, it does not matter. Okay. Whereas, but after that, you reach that you have got a vehicle on the left. Now your action towards right will be better. So in both, we have to decide differently. Okay. So it is that in many game state, it does not actually matter which action you take. For example, we are playing a racing game on a straight empty road, whether we move slightly left, right, or it does not matter. So in if we apply a standard DQN, so then what will happen that for every action which is not mattering, but I have to update my Q value. So in dueling DQN, what happens? We are decoupling the value of the state from the advantage of each action. So we have got something called advantage. Okay. So it learns that road is good once and separately learns if moving left is better than moving right. Simple example, like a restaurant review. So we have got two things in that. One is the state value V. V means how good is the restaurant overall. V tells me, okay, this restaurant is good. Action advantage is that in that restaurant, if I order pasta in comparison to salad, that how much better is pasta to the salad. That is the higher intuition of your dueling DQN. So I'm on a road. First of all, I want to know how good is the road. One. Second, on that road now, when I know it is a good road, I want to know what is the advantage of taking action towards left from right. So these are the two things. So in this, what do? We maintain two networks. One is known as value stream and another is known as advantage stream. So from the value stream, I get the VS. From the advantage stream, I got AS. And the formula is very, very important. Then there, we join them, we aggregate that. And the formula is QSA is equal to VS plus advantage. So, and when we use a mean centering formula, then QSA will become VS plus ASA minus 1 divided by A into summation of A. So these are the two formulas, please remember, from the quiz point of view. Okay. Now there are certain parts, okay, which are there, that A star, expectation of A star which will be there, it will always be 0. Okay, so this was the dealing SQN, DQN, sorry. Shall I cover it again for everybody's comfort? Anybody wants me to repeat this? Okay, so I will take that. No, so there are very, very less questions on in week 7. So this is a question on tile and all that. So here there are two tiles. If you see tiling 1 and tiling 2, and they had asked in the question what is ST plus 1 minus ST. So when you take ST plus 1, so you can see in this is tiling 2 W18. So it is W18, and from tile 1, 1, 2, 3, 4, 5, 6, it is W6, or it is ST plus 1. Okay, it is in W5. So ST plus 1 is W18 plus W5, whereas ST is W14 plus W5. So when you subtract, it becomes W18 minus W14. There are some involved questions in PYQs. Now, with this, I have finished till week 7. Week 8, I had shared the document, revision document with all of you. I will not go through that. Now, immediately we can jump on the PYQs. Is that okay with all of you?
Yes, sir.
Okay. So we'll take some, okay, for on policy SARSA update rule, as A, S dash, A dash are needed. When is A dash computed? Okay. So the formula is very, very simple. QSA. So we fix the A dash before updating. So here we are fixing this. Okay. So it is happening before we update this. So it will happen before updating QSA. Okay. Consider TD lambda learning in reinforcement learning. Which of the following statements accurately describes TD lambda learning? So TD lambda, first of all, we should know the formula. So from the formula itself, your first option which is there, it is correct. Okay. And now with TD lambda, with lambda is equal to 1, performs updates only one at the end of each episode. That is the MC, but this is incorrect. Why? Because we had seen that when we use TD lambda with eligibility trace, it updates at every step. So that's why the second option is incorrect. When TD lambda with lambda is equal to 0, it reduces to one step TD learning. So that we had seen. You reduce lambda is equal to 0 and it will become your TD, one step TD learning. You can go through this discourse here. It has been discussed there. Now in TD alpha lambda learning, what is the role of eligibility trace? So role is what? That I come here and then I keep on updating all the values. So I keep on telling which state was important due to which I have reached here. So when we see the options here, what are the options? The eligibility trace is used to store past observation and actions. No. Determines the learning rate. No, there is nothing in learning rate. The eligibility trace helps in determining which state action are eligible for updates. So this is the most appropriate. Okay. Now, what is the key advantage of using n-step TD prediction over one-step TD prediction? So n-step TD prediction requires less memory, which is incorrect. N-step TD prediction can handle delayed rewards and credit assignment over multiple 10 steps. So this is the most suitable answers. N-step TD prediction converges faster to the optimal policy. No, because it is quite long. N-step TD prediction guarantees convergence to the optimal value function for any choice of the learning rate. So there is nothing learning rate in that, and this is incorrect. Okay. Consider a reinforcement learning agent navigating a complex environment with sparse rewards. So this is a very, very important language which is straight away taken from the slide. So here, when we have got a complex environment with rewards, then always what will be the, which of the following statement accurately describes a key advantage of using double DQN? So double DQN will be double Q learning helps to reduce the variance. So when we used double DQN, it will always help to reduce the variance. So that will be the answer, and it is straight away from the slide. So this is the answer first. Now these are some questions which look very, very tricky, but when you go through them, it becomes very, very easy. Consider training an RL agent to play a copter bird. The bird moves horizontally at a fixed pace. So it is moving like this, fixed pace. There are three actions: up or down, or do nothing, or just do nothing, keep on going. Passing obstacle pipes through the gaps gives a reward. So when you pass through this, gives a reward. Hitting an obstacle ends the game. So they are moving. In this easy variant, we have the obstacle placed quite far away from each other. So here this distance is very, very far away. So this is very, very similar what we learned in dueling DQN, that here it does not matter in this phase whether I go up, whether I go down, or I be here. So for this, the best value-based method will be a dueling DQN. That is the advantage of dueling DQN. Okay. Consider the following DQ network with three layers, ID 0, 1, 2, 3, starting from left. So they are starting from left, and 1, 2, and 3. So recall the linear approximator view of DQN. At which layer are the features for the states calculated? So where we do the calculation of the features, we are doing the calculation at this here. Here it is only the feature extraction. So this will be 3. Okay. Now this was a question where I had told you that we will discuss this question. So we can do that. Here the discount is there. So we have to find the Monte Carlo, and then we have to find by the batch TD, and we will see the MDP also. Shall we solve this question?
Yes, sir.
Yeah, okay. Okay, so let's do for MC. So here remember gamma is equal to 0.8. Okay, so for episode 1, value of A is equal to reward of 2 plus gamma into value of B, which is 0. This is 2. Value of B is equal to 0. Episode 2, I'm solving for Monte Carlo. Value of A is equal to 0 plus gamma 0.8 into 1 is equal to 0.8. Value of B is equal to 1.
So the doubt in this question was asked by someone was that sometimes we calculate it like this and sometimes we directly take the average. So
No, but here gamma is taken, na? So we have to consider this discount also.
okay, and if gamma is 1,
Then directly you can take average.
yes.
But average means see A0 to B1, here VA will be equal to 1 with this non-discount. Okay. So episode 3, let's see. VA is equal to 2 plus 0.8 into 0 is equal to 2. VB is equal to 0. Episode 4, VA is equal to again 2. VB is equal to 0. And then VB is equal to 1, 0, 1 and 3. Therefore, Monte Carlo VA is equal to 6.8 divided by 4 is equal to 1.7. And for VB will be equal to 1, 2, 3, 3, 6 divided by 8 is equal to 0.75. Now, when we calculate for TD, now let's do for TD. Now here it will become VA is equal to 2 plus 0.8 VB plus 0 plus gamma TD, gamma VB plus 2 plus 0.8 VB plus 2 plus 0.8 VB. So this will become 6 plus 3.2 into VB divided by 4. Now VB will remain same. So this will become 6 into 3.2 into 0.75 divided by 4. You calculate this, you'll find the answer. Okay. Any question on this? Okay, any doubt? Anyone?
No, sir.
Okay. So we can solve this. Okay. Now this. So already I have written here that this is an important question. Please practice this because in all the PYQs this question has come. Okay. Now this question is, you are given an MDP with 3 state S1, S2, S3. The values have been given. And 2 actions A1 and A2. The design of the functional approximator has been given here. Okay. The first question they are asking, so this is a good question. We'll solve this question. Okay. It is quite a long question also. So first they're asking, VS is a linear function approximator. So is this a linear function approximator? We know from our ML experience that yes, it is a linear approximator. Now recall that, can somebody mute his mic here? I think somebody's mic is on. Yeah. Now recall that one can implement semi-gradient descent in the computation of the gradient error. The equation for the TD0 error is given below. This is okay. Which of the following is or are considered constants when computing with respect to W this square? So we know when we had discussed that when we were taking R plus gamma into VST plus 1 minus VST square. So what we had done, we had considered these two values as constants. Okay, and that's why when we took delta JT, it become this entire minus 2 into delta into phi ST. Okay, so these are the two are taken constants. Okay, now they are asking recall the SGD update rule for the TD0, the same half learning square W square. Update W for the experience S1 A1 minus 3 S2. Okay, so this is the very important thing. S1 A1. So I am taking S1 action. I take A1. I get a reward minus 3 and I am reaching S2. And I have to update the W's. So first of all, I have to know what are the values of W's first. So initially all W's are 0. Okay. And I have been given alpha is equal to 0.1, gamma is equal to 0.9. So first step in this, when I want to calculate this, I want to calculate first TD error is delta. Delta is equal to R plus gamma into V, I'm reaching S2 minus V S1, or this I can say Q. Now this Q S1 and S2 which are there, I will calculate as per this formula. Sorry, here it is B. Can we calculate this again? Any problem with this question? So if you think this all W's are 0, so this is also 0, this is also 0. So TD will be minus 3 only. Is this okay with everyone?
Yes, sir.
Okay. Now, what we know the formula WT plus 1 is equal to WT plus alpha into delta into phi. This was the formula.
Yes, sir.
So we have calculated this. This has been given 0. Now we need only phi. Now phi is what? Phi is this 1 S square S cube. And this phi is with respect to what? Okay? This is with respect to S1. So this phi will become phi is equal to phi of S1 is equal to 1, S is 1, S square is 1, S cube is 1. Okay. So this will become WT plus 1 is equal to W2 is 0, 0, 0, 0, 0. Plus alpha value is what? Alpha is 0.1. Reward is how much we got? Okay, this value TD error was minus 3, and then we put 1, 1, 1, 1. Okay, so this will become, if you calculate this will become minus 0.3. So this will become minus 0.3, minus 0.3, minus 0.3, minus 0.3. And we have to enter the sum of the components. So sum will become minus 1.2. Is that okay with everyone, these calculations? Understanding?
Yes, sir.
So this question, if you solve this correctly, you will get 12, if I'm not wrong, I think 10 marks or 12 marks. Okay. So it has got first this part, approximation, then it has got second this part, and this is the third part. So please be ready for this kind of questions. They will definitely come. Okay. So this is from week 7. Okay. They have also asked, okay, now calculate VS2W. So now see, now S2 we know, and use W obtained from this. So S2 is -2. So your phi was what? Was 1, then S2 -2, then S2 square 4, and then -8. And W you have got -0.3, -0.3, -0.3, -0.3. So what you have to do? Just you have to multiply this phi transpose into this. So this will become 1 into 0.3 minus 0.3, minus 2 into 0.3 plus 0.6, minus 1.2 plus 2.4. You add this and you get 1.5. So this is total 12 marks question. Okay. So if we solve it, we get all the answers. Okay. Now recall the incremental update rule of reinforcement learning. So this is basically from week 8. So week 8, what we have done in the week 8, the topic which is there, that instead of updating these value functions or the Q values, why don't we update the pi? So from there, the formula which came, that if we want to update the pi, so from there, we have got delta theta t is equal to alpha RT into gradient of pi. So I will just do here that if we are updating a pi, then theta is equal to t plus 1 is equal to theta t. Here it is very, very important that here it is a gradient ascent plus alpha into r minus baseline, which is generally we take r bar, and gradient of logarithmic of pi theta. So this is the formula. Now, what they have given in this question, that we have got a binary banded problem where pi theta a is theta if a is equal to 1, and pi theta by a by is equal to 1 minus theta. Now, if we consider this, then we can write this as that logarithmic of pi theta a is equal to a minus theta. This is gradient ln pi theta into theta into 1 minus theta. So let's check this. Please remember this formula. This is very, very important. So see, when pi is equal to theta, when a is equal to 1. So in this case, what will be gradient of ln of pi theta? This will be 1 by theta. Ln of theta is 1 minus theta. And if you put here a is equal to 1, so this 1 minus theta, they cross, and 1 minus theta is the correct answer. And when theta is equal to 0, this becomes 0 minus theta over theta into 1 minus theta is equal to 1 over 1 minus theta. So 1 minus theta, this is also correct. When you take gradient of logarithmic of 1 minus theta, this will become 1 minus theta and minus theta minus 1. And this is minus 1. Okay, 0 minus theta. So please remember this formula, that in case of a binary banded problem, this is the one. Okay, I have written here also. So you get this a minus theta over theta a minus theta, which is coming from here. This is the part which is right. And it is 1 minus theta if a is equal to 1, which is coming from here. And it is minus 1 over 1 minus theta, which is coming from here. So these two options are right. So I will just cover very, very quickly week 8 concepts. So here in the professor, he had covered 3 policies. So first of all, we have to update the policy So for that policy, if policy has got parameters theta, so then theta plus 1 is equal to theta t plus alpha into r minus baseline and into gradient of ln of pi. This is first formula 1. Very, very important. Why we use baseline? This is a baseline. So when we get reward, we also use a baseline. And if you remember PA3, we had done with baseline and without baseline. This is this baseline. And generally, what do we do? Generally, we can take R bar is equal to baseline. So whatever the average is there, we do this. And why do we use Y baseline? Y baseline is to reduce variance. Otherwise, with every sample, your variance will be very high. So this is the first formula. Now, we have got 3 cases where one pi can be this, where it is a binary that pi theta a is equal to theta if a is equal to 1, 1 minus theta a is equal to 0. So this is a binary problem. Binary problem. Okay. And now for this problem, we can write gradient of logarithmic of pi, because we have to calculate this gradient. We can write this as a minus theta divided by theta into 1 minus theta. And when you plug in this a and 1 and a is 0, you'll find it perfectly works. So for example, a is equal to 1, then logarithmic ln pi, as per this, will be equal to gradient of ln of theta, which is 1 minus theta. And here, if you plug in a is equal to 1, it becomes 1 minus theta over theta. 1 minus theta is equal to 1 over theta, which is matching. Similarly, for a is equal to 0, it will become dou of dou theta ln 1 minus theta, which becomes minus 1 over 1 minus theta. And if we plug in here, it will also become 0 minus theta, theta 1 minus theta, theta cancel, and it becomes minus 1. So this is a general formula for the binary bandit. Now, the second is we can have pi as a softmax also. Softmax. So we have learned that if we have got theta and we have got AI, so this is some policy. In softmax, how we used to choose an action? E of theta I divided by summation of E theta j. Okay. So when we take logarithmic of this pi, theta I, this will become theta I minus logarithmic of summation of E theta j. Now, when you take delta of delta theta I of this pi, this will become 1 because we are taking with this, and this will become, if you just abbreviate this, so this will become, is everybody with me what I'm solving?
Yes, sir.
Yeah. Okay. When you take this derivation, so this will become ln, this will become summation of E theta j, and on top, if you see, this E theta summation is nothing but E theta 1 plus E theta 2 plus E theta I plus up to E theta j. So see, when I take with respect to dou by dou theta I, everything will cancel out, only E theta I will remain. Okay. And this is nothing but it is your pi. So this becomes 1 minus pi theta I AI. Okay. So, but when we are doing this, when we are doing for theta I and AI, we will also update theta j. So for theta I, update rule is theta I plus alpha into r minus baseline. This will become 1 minus pi into theta I AI. This is 1. Now we have to update theta j also, other thetas also. Now if we do this, if I do a derivative with respect to theta j, this will give me 0. So here this will become theta j plus alpha into r minus pi, and this will become minus pi theta j aj. So these how we update the thetas in a softmax. And the third professor had covered that in case your pi is coming from normal distribution. So in normal distribution, you have got mu, and you have got sigma, and you have got, for example, theta. So it means that your pi is equal to 1 over root 2 pi into sigma e to power 1 minus 1 minus 2 theta minus mu square over rho square. Okay. So when I take ln of pi, if I take ln of pi, this will become minus 1 by 2 theta minus mu square over rho square minus ln of root 2 pi sigma. Now when I take for mu, I will take derivative with respect to mu of this ln pi. So this second term will be 0, and this first term will become minus 1 by 2 this square into 2 into theta minus mu and into minus 1. 2 will cancel out, minus 1 cancel out. So this is proportional to theta minus mu. Is this okay? So from here, if we expanded, so your mu will become mu plus alpha into r minus b into theta minus mu. This is for this. And similarly, you can do for the rho also. For rho also you will get. So these are the three main concepts which are covered in your week 8. Okay. So this next problem is your tile problem. Tile, okay, you can do that. So in this tile coding, so they have got blue tile, black tile, and brown tile. So how many tiles which are there? First of all, what they have asked. So let's understand this question. Consider the following continuous state discretization problem. Performing tile coding converts this R2 into a 0 to 1 d-dimensional. That either you will have 0 or 1. That is a d-dimensional binary vector. So what is the value of d? First of all, we have to know this. So see, for finding this d, what we have to think that every state can be considered as combination of all these tiles. Now in these tiles also we have got different weights. Like blue 2 into 2 tiles, so it will have 4 weights. W1, W2, W3, W4. Black, it will have 9 weights. Brown, it will have 16 weights. So total encoding which I have to do is how much? 16 plus 9 plus 4. Is that understood, Ravina?
No, sir. Why we haven't taken the max out of it, sir? The like brown tile should be taken, I think.
No, see.
Why we are summing it up, sir?
No, summing. No. It is not summing. See, there is one tile here, S3. S3. Okay, there is one state. It is coming in this tile also. It is coming in this tile also. It is coming in this tile also. So now I have to represent this. So see, blue had 4. So blue I can represent as W1, W2, W3, W4. It means it has got 4 states. Another one, black, has got 3 into 3, 9. And brown has got 4 into 4, 16. So it means any state which is there, how to represent that state? I have to represent that blue W1 is there.
But sir, you told that it is represented by one hot encoding. So we should take all the possible states and then 100 like this.
No, no, see, not the states. See, for example, in this state, I have got only W2. So I will represent as 0100 from blue. Then I have got in black. In black, I have got only, for example, so black has also got 9 weights. So this will be 9 length. Then brown, it will have 16 length. So this is one hot encoding to consider all the tiles because it can have combination from all the tiles. Na? So this encoding which is there, it will be 16 plus 9 plus 4. Okay. Anybody else is doubt? Okay, no problem. Now the second is a question again we'll understand. Now for any state S which is belonging to R2, so here is the S.
Sir, one question.
Yes.
In this tile encoding, we always do one hot encoding, right? Means, every time the question will come will regarding it will be only one hot encoding, like.
So you will have to consider these weights which are there. Okay. So see, this has got blue has got 4 weights, black has got 9 weights, brown has
Yeah,
got
yeah, sir.
16 weights.
That I understood. That,
Yeah,
like for example, for blue we have taken 4, and after that we have taken 9 bits for that.
yeah.
That I understood. But in such question, only bits means we will get only bits, right? There will not be any continuous thing.
No, no. Okay.
Okay, okay, I
Okay.
understood.
Now the next question is very, very interesting. Please pay attention. For any state, what is the number of on bits in its corresponding discretization representation? If you believe the number of on bits is not constant and depends on S, enter -1. So for this question, what they're asking that for any state, what we can represent that tile 1, tile 2, or tile 3. Okay. So if all the 3 tiles are there, I can represent 111. Only tile 1 is there, then only tile 3 is there, 001, 010. So I can have for 3 tiles, this is the place that I will have 3. Okay. Now consider the tile coding representation for the points marked 1 and 2. What is the dot product of these two representations? So this I will just zoom in. So see 1 and 2. In 1 and 2, I have just we have discussed that 1 and 2 will have a dimension 29. So see which all when you do a dot product means that it will give you a result which has got common weights. If the weights are not common, the multiplication will be 0. So we have to find in a dot product that 1 and 2 which all weights are common. So can we check that? For example, in blue we have got W2 common. Is that okay with all of you?
Yes, sir.
But in black they are not common.
No, sir. In black also not W2 and in black the third one is common with blue.
Not blue. See what we have to see. We have to check how many are common in blue, common, black common, or brown common. So in blue, you have got only this common. This is common. In black, if you see this and this, they are not common, separate.
Yes, sir.
Similarly, in brown, this and this are separate.
Yes, sir.
So when you will have the vector which is there for 1 and 2, it will be matching only at one position for blue.
Sir, in here,
I have
common
one.
means what? Common means we are looking at what?
See, when we are representing, okay, just hold on. Just okay, I will just explain. Common means, see, when I represent a point 1 and point 2, so it will represent blue W1, W2, W3, W4 for blue.
Yes.
Then it will consider, for example, W5 to W14 for black, and W15 to W31 for brown.
Okay.
Okay. Now C for one, if you take W blue, then it is W1 is 0, W2 is 1, this is 0, this is 0. So this is 0, 1, 0, 0.
Okay.
So this is 0, 1, 0, 0.
Okay. So that point one comes under which
Yeah.
uh,
Okay. What is the combination? Similarly, in black, if you see what is a black, so black is in number one is, for example, this is W5, W6, W7. So this is W6. So this will become 0, 1, 0, 0, 0, 0, 0, all zeros. Is it okay? And this is 0, 0. Okay. And similarly in brown, if you see, now brown also I give some numbers. So in brown also, this is 1, 2, 3, 4, 5, 6. So this is this point, this one. Okay. So this is 0, 0, 0, 0. So this will be 0, 0, 0, 0, 0, 1. Rest all zeros. Is this okay?
yes.
Now, when you represent 2, it has also got 0, 1, 0, 0. But here, this number which is there, it is having different.
Yes.
Okay, here also it is different. So now when you do a dot product, rest everything will cancel out, only this will multiply, this will
Yes.
give 1.
Mhm.
So remember the dot product will be equal to number of shared weights. Okay, so that is a shortcut.
Okay.
Okay, Ravina, is it clear?
Yes, sir.
Okay. Okay. Now, next question is, they have given 4 episodes, and what they are asking that using the first visit Monte Carlo, find the estimated value of the state S. So, first visit means, so first visit, this is S, ABSCS. So, ABS here only from the first visit, and the returns received are the first visit. So, here it is 4, it is 1. So, we will take only 4. Here it is 2, here it is 3, it is 5 divided by 4. This will be first visit. If we take all visits, then we'll add 1 and divide by 5. That is a concept here. Then we come to next question. Okay. Okay, consider a simple problem where an agent is navigating a grid world to reach a goal state. The agent receives a reward of +10 when it reaches the goal state and 0 otherwise. Okay. The grid is a 3 into 3 with a goal state located at 2 into 2. So this is 0, 1, 2, 0, 1, 2. This is the terminal state. Here reward is 10, rest rewards are 0. If the agent moves out of the group, it stays in the same position. Policy, the agent follows a fixed policy where it always moves towards a goal state. It is always moving towards the goal state. Learning parameters, they have given discount factor 0.9, learning rate 0.1, for TD 0. Following are the trajectories. It goes from 0, 0 to 0, 1. So it goes here. Then it goes to 1, 1. Then it goes to 2, 1. And then it goes to 2, 2. And they have given reward plus 10 at 2, 2. So this is the first trajectory. Second trajectory they have given 0, 0 to 1, 0. Then to 1, 1. Then to 1, 2. And then it comes here. And third trajectory, it goes from 0, 0 to 1, 0. Then it goes to 2, 0. It goes to 2, 1. And it goes to 2, 2. Okay. So these are the three trajectories. So what is the estimated value of 1, 1 using the Monte Carlo method after these three episodes? So for Monte Carlo, what do? We have to find estimated value of 1, 1. So 1, 1 is only in this episode and in this episode. So what we will have to do for finding 1, 1, value of 1, 1 is equal to reward moving to 2, 1, which is 0, plus gamma, which is 0.9, into value of 2, 1. Value of 2, 1 we don't know presently. So this is 0.9 into value of 2, 1. Value of 2, 1, now we calculate, is equal to, it goes from here to here, 0 plus, 10, reward is 10, and 0.9 into 0 is equal to 10. Therefore, value of 1, 1 will become 9 for first episode. Is this clear with everyone?
Yes, sir.
Okay. Similarly, in the second episode, it will become 9. And in third, 1, 1 is not there. So for the MC method, it will become 9 plus 9 divided by 2 is equal to 9. Is that okay? The question is looking lengthy, but if you understand the concept, then it is very, very short, very easy to solve. The second part of the question is, so there is a lot of discussion on discourse, and finally I shared my solution, which Rohit has answered that it is the correct solution. What is the estimated value of state 1, 1 using the TD0 method after these three episodes? So in the TD method, what happens? In the TD method, we initialize Vs is equal to 0 for all S. So starting, so we have got three episodes. In the third episode, we don't have 1, 1, but we have to find. So what happens in episode 1? We go 1, 1 to 2, 1 and then go to 2, 2. And the reward they have given. So we finally, again, we solve V21 is equal to 0 plus alpha TD formula reward plus gamma into V22, which is 0. So this becomes 1. And with respect to this, now we calculate V11. V11 will come 0 plus alpha, reward is 0, gamma into V21, which becomes 0.09. So after first episode, V11 is 0.09, V21 is 1. These are the values. In second episode, we go from 1, 1 to 1, 2 and then to 2, 2. So again, V12 we are going for the first time. We get V12 is equal to 1. Now V11 will become V11 plus alpha into reward to 1, 2, which is 0, into 0.9 into 1 minus 0.09. So if you calculate this, you get 0.171. So after episode 2, now we have got V11, 0.171, V21 and V12. Now in episode 3, there is no 1, 1, so we don't have to calculate. Okay, so finally we get V11 equal to 0.171. Is that okay with everyone?
So can we take a break, sir?
Yeah. Okay. For 2 minute, 5 minutes break. I want to finish it again. Maybe another 15 minutes. Okay. Shall we take a 5 minutes break?
Yes, sir.
Yeah. Okay. Thank you. Hi, can we start?
Yes, sir.
Okay. 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 Now you are using a TD0 algorithm to estimate the value function. The current value estimates are this. During an episode, the agent transitions from S to state S dash and receives a reward of 4. Learning rate is zero point 0.1, gamma is zero point 0.9. What is the update value estimate for VS? So very easy. Okay, we can do that, no problem. Now we are using a Q learning algorithm to find the optimal policy for an environment. The Q values for state action pairs are given in the table below. And during an episode, you transition from state S to S dash after taking action A2. So here we have taken A2. The reward received for this transition is 3. Learning rate is zero point 0.1. The discount factor is 0.95. What is the updated Q value for QSA2? So see, at S, we take action A2, we get an reward, and then at S dash, we will take the best action, which gives me the maximum Q. So what is that reward? The Q value, that is 9. So 9 is the maximum. With that, we calculate. Okay. Consider TD lambda. So what is so this is a repetitive question. TD lambda in a reinforcement learning, what it does? It is a weighted average. That is correct. Lambda is equal to 1 at the end of episode. No, because with the traces it can be done. With lambda is equal to 0 reduces to 1 step TD learning. That is correct. So A and C are correct. The role of eligibility trace, it was a repetitive question. Advantage of any step TD prediction, again, that what is the key advantage of using a target network in deep Q network? So this, remember, we had two problems. One was high correlation and second was non-stationary target. So when we take target network, we convert this non-stationary to stationary. So the target network stabilizes the learning process by providing a more consistent target for Q value estimation. In the context of deep Q, how does experience replay contribute? This is nothing but buffer. So it breaks the temporal correlations in the data. How does the choice of function approximator impact the performance of policy gradient method? Function approximator means that how you'll be aggregating. So function aggregator, we had binary, we had softmax and all that. So basically the choice of function approximator affects the stability, convergence rate and generalization capabilities of policy gradient methods. How does the inclusion of a baseline in the reinforcement algorithm impacts its learning? So remember the formula. Uh, in a baseline, we had theta is equal to theta plus alpha into r minus baseline into gradient of logarithmic of pi. So this baseline reduces the variance. Remember this, reduces the variance. In dueling DQN, what is the primary advantage of decoupling the value function into state value and advantage value? So we have got two networks, one gives me VS, another gives me AS, and then we aggregate that to get QS is equal to VS plus AS. So what it does, it decouples the value function, allows dueling DQN to better handle scenario where certain actions are consistently advantages or disadvantages across states directly from slides. Okay. Okay, now I feel like I will leave this question paper to all of you. Now I think we should finish this. Okay. So there is only one question paper. Go through this in case of any doubt. Please, you can post on WhatsApp and I'll be answering. Okay. So because majority of the concepts we have covered. Any question which you feel that I should cover?
Sir, please share the updated this paper also.
Yeah, I'll share that. Okay. Thank you for joining in, and thanks, and wish you all the very best. Do well. Take care.
No
All the
worries, sir.
best, sir.
You.
Bye bye.
Thanks,
Bye.
sir.
Bye
All
bye.
the best.
Bye.